Dear students, this lecture has been delivered in favor of Sri Ramakrishna Institute of Science and Technology for this course Diploma in Mechanical Engineering second year 4th semester. Subject Manufacturing Process 2, Chapter 1, Part 1. Lecture delivered by Devaprasad Mukhopadhyay, DPM sir. The next slide, or the first slide, it shows the kinematic diagram of a lathe. If you study closely this diagram, there is a gearbox, which is the speed gearbox in the headstock, and there is a feed gearbox below that. The power enters through the speed gearbox from a belt pulley drive on the left hand side of the drawing, and then it goes into the gearbox for a range of speeds to take care of different cutting conditions. Now, in the next slide, we will see the inside arrangement of a 12-speed gearbox. There are 4 shaft lines which is shown in this particular drawing, and you will see that in the first line, this is a 12-speed gearbox. In the first line, there is a clutch which is disengaged and engaged when you require power to the gearbox and when you don't require it. Then, there is on the first line shaft, input shaft, there is a cluster. There is a cluster gear on the first shaft consisting of 3 gears which are sliding, and the three gears matches on the 3 gears on the second shaft. So if we have 1 speed in the first shaft, input shaft, we will have 3 speeds on the second shaft. And on the second shaft, there is a cluster of 2 sliding gears, which matches with 2 gears on the third shaft. So we will get 3 into 2, 6 speeds in the shaft 3. And then there is another cluster of 2 gears, which actually transmits the power through 2 gears on the output shaft. So we will get 6 into 2, 12 speeds on the output. If we go to the next slide, we will go to the process of taper turning and how the taper turning is done, how the set over is calculated. That is being described here. The taper turning is done in this process where the tailstock set over method is used. The tailstock is actually pulled horizontally to a distance of S, which is called the set over, depending on the taper angle we require. In the sketch, the S is shown and the degree of taper alpha is also shown. In this condition, if the object is machined, then taper will be generated on its surface. Now, geometrically, if we study this drawing, this triangle A, B and C, the perpendicular is drawn on the previous center line, on the headstock center line, and it meets the center line at C. So BC is equal to actually S, the tailstock set over. Now in the triangle ABC, we have BC as the perpendicular and AB as the hypotenuse. AB actually is the length of the job which is held between centers, total length of the job, which is capital L, and small l is the length on which the taper is drawn. And bigger diameter of the taper is capital D, smaller diameter is small d. So if you go into the calculation, triangle ABC, BC is equal to AB sine alpha. Now BC is equal to S and AB is equal to capital L. So we can say S is equal to L sine alpha. That is the set over. Now when alpha is small, sine alpha is equal to tan alpha. So S is equal to L tan alpha, and which is L capital L into D minus D over twice L is the formula for set over. Now when L is equal to L, when the total length of the object is cut as a taper, then L becomes L, so S is equal to D minus D by 2. So when you have a full length taper, you have to deduct the major diameter, deduct the minor diameter from the major diameter and divide it by 2 to get the set over. So the different figures are: capital L is equal to length of the shaft in full, small l is the taper portion, alpha is the angle of taper, and d minus d by L is the conicity or amount of taper. D minus d by L is the length of taper. That means the difference in diameter divided by the length of the taper. It gives you the conicity, and S is the set over. So in the next slide, we will go to some problems on set over. And the first problem says that a shaft 1200 millimeter long has taper of 1:200 for a length of 600 millimeter. The maximum diameter of the shaft is 75 millimeter. Determine the minimum diameter of the shaft and the amount of set over. So what we know here, we know amount of taper here, which is a conicity, which is 1 by 200, and which is capital D minus small d by L. Small l is small l is the length of taper, which is actually 600 millimeter. Capital D maximum diameter is 75 millimeter. So, and conicity is equal to 1 by 200. Capital L is 1200 millimeter. So 1 by 200 is 75 minus d by L, which is the formula for conicity, and small d is 72 millimeter. Now set over is L into d minus d by 2L. We know capital L 1200 into 75 minus 72 by 2 into 600, which is 3 millimeter. The next problem says determine the amount of set over required to turn a taper in the entire length of the workpiece, having diameter of large n 30 millimeter and that of small n is 20 millimeter. So very simple problem. The set over we know, when the full length taper is there, then it is d minus d by 2. So S is 30 minus 20 by 2 and it is 5 millimeter. Now this ends. We come to the end of part 1. We'll go to part 2 now.